Hello, everyone, and welcome to Salesforce Apex Hours. My name is Elkin Cordova, and this is Introduction to Encryption for Salesforce Professionals. Thank you so much, Amit, for having me in this session. It's a great honor. A little about myself. I am a Salesforce consultant, developer, and architect at Globan. I am the leader of the Bogotá, Colombia Trailblazer Developer Community Group. I have 5 years of experience in the platform and previous background in electrical engineering. You can contact me at these social networks. Today's agendas will be, first, we will see what are the problems we are trying to solve with encryption. Then we will see how encryption works. Then we'll see how Salesforce uses encryption for his purpose inside the platform. And at the end, we'll see some tools and references for you to check later. The first problem we face every time we try to use internet is intersection. So let's see with an example. Imagine we have two people, Bob and Alice. So Alice is going to send a message to Bob. Here we can see the message represented as an envelope. So Alice sends the message through internet and Bob receives the message and opens the message. But what happens if there is a hacker in the middle? If the hacker do intersection, the hacker can see the message and open the message. Next issue is falsification. So we have again Alice and Bob. Alice is going to send the message. She sends the message, but the hacker intersects the message and opens the message. But this time not only open the message, but change for a different message, a malicious message. So the hacker sends this different message to Bob and Bob opens the message. So he cuts the issue. Next scenario is repudiation. So imagine Alice and Bob again. Alice sends the message and Bob opens the message. But suddenly the message is not trusty anymore, because even though we thought that Alice sent the message, in real life, the reality was that the hacker sent the message and passed as Alice. But at the beginning, we thought it was Alice. So at this point, we cannot trust who sent the message. And the last scenario is like the most common scenario that happens every day. People don't take into account if opening a message can cause problems. So this is named spoofing. So originally, the hacker wants to send the message, the hacker sends the message, and any user without knowledge about what could happen in the internet, we will open the message. So this is the most basic issue with when we try to access any protected resource in the internet without us being cautious if open or not. Okay, so how can we solve this issue? There are different strategies, but basically we want to use this. So at this point, encryption appears. So imagine again, Alice and Bob wants to communicate. Alice sends the message, but this time she is going to use a lock and a key. So graphically, you can imagine that Alice has a box and puts the message inside the box and close the lock with the key. Send the message, she sends the key, and Bob is able to open the message with the key that Alice sent. And this time, the hacker could not open the message because the hacker doesn't have the key. So now we are going to see how this can be implemented. We are going to see the first type of encryption that we can use. This is called the shared key cryptography or symmetric cryptography, because the key that we use to close the box is the same key that we need to use to open the box. So we can see with Alice and Bob, Alice is going to create a key, send the key, and Bob receives the key and open the message. But if it is not easy to send the message without any hacker intercepting the message, how can we send the message, the key also? So even though we are trying to fix a problem, now we have a different problem, how to send the key. So we have some type of algorithms to follow to do this. One of the most famous is the Diffie-Hellman key exchange that is based also on the work of Ralph Barkley. So let me show you with an example. We have Alice and Bob. Alice is going to create a public key. We are going to represent in red. Alice is going to send the public key to Bob. This key can be intersected, can be stolen by the hacker, but we don't care because we have a different strategy to obtain the key. This is not the key that we are going to use to encrypt the message. So now Alice is going to create a new key. This is going to be a private key that only Alice knows. Bob is going to create his own private key. And then each one is going to add the public key with the private key that they have created. Using colors, we can see that red plus blue is like purple, and red plus green is like brown, some kind. This is, at this point, I am showing an example using colors, but in reality, we are using mathematics. For example, we are using prime numbers, the Fermat's little theorem, and the discrete logarithm problem. The factorization of prime numbers and the discrete logarithm problem are very difficult problems to solve that not even having a big computational power, it's easy to solve. So until someone can exploit this kind of problems, we are safe. Okay, so let's continue with the example. So Alice now has a kind of purple key and Bob has a kind of brown key. They are going to interchange. So Alice is going to send the purple and Bob is going to send the brown. And then they are going to again add those keys. Mathematically, you can see that their result is going to be the same. So Alice and Bob now have the same key, but the hacker cannot recreate this key because the hacker does not have access to the private keys, only has access to the public keys and the keys that were mixed, the result of mixing the original keys. It's very difficult to obtain the two original values that got this value mathematically. So this is the importance of the Diffie-Hellman key exchange. So, okay, now we have a way to send a key to encrypt our messages. But there is a different way to do this. So now it appears the public key cryptography or asymmetric cryptography. Here, we are not going to use the same key to encrypt and decrypt the message. We are going to use two different keys, a public key and a private key. The public key is going to be used to encrypt the message, and the private key is going to be used to decrypt the message. So let me show you with Alice and Bob again. So here we have Alice. She is going to send the public key. So imagine this is like the box. We are going to send the box open. So Bob can insert the message that he wants to send to Alice to read. So previously we were using Alice to send the message and Bob to open the message. But now we are going to change a little bit. So Bob is the one that is going to send the message. But Alice is the one that is going to send the key. So Bob has the key, place the message inside our imaginary box. So in reality, it's encrypting the message using the public key that Alice shares in advance. And then send the message, encrypted message, and Alice has a private key that was not shared with anyone and open the message. So this is why it is asymmetric, because the key to encrypt the message, the green one, is different than the red one, the private key. So this solves a lot of the initial problems we saw. So here we don't need to share a public key. The key cannot be stolen, and we have all the benefits of encryption messages, encrypted messages. This, in reality, this is done via some kind of algorithms. We are using a lot of mathematics, high-level mathematics. For example, modular exponentiation, the Euler-Tauchen function, and some basic algorithm that we learned in our initial studies, the extended Euclidean algorithm. I'm not going to explain all of this, but you can think that breaking this kind of security needs a lot of study, to learn, a lot of study to break this kind of security. As before, we are using the problem of breaking big numbers, composite numbers, into the original prime numbers. With the computational power that we have at this moment, it's very difficult to break bit composite numbers. We expect that with the new computers, new computer power from quantum computers, this can be broke, but there will not be a computer like that in, for example, 10 years. But at that point, we expect that new algorithms, new ways to secure our data will be available. So this is the option we have to keep working on this topic. Okay, so I'm going to show you now a benefit of using the symmetric algorithm. Previously, when we were using the symmetric cryptography, we imagine you want to talk with Alice, want to talk with Bot and with Caroline, for example. If she wants to use the same key, she cannot use the same key. She needs to create different keys for every person. So with the asymmetric cryptography, we can have the same key for encryption and decryption, and will still be safe. Let me show you. So Alice is going to share the public key. So it is public. It doesn't matter if someone has access to the key, and send to different recipients. Each of these recipients are going to create a message, encrypted message, and send back to Alice. So with the same public key, we will see that they are going to encrypt the different message and send back to Alice. Alice is the only person that has access to the private key, and it's going to open all the locks with the same key. So this is an added benefit of asymmetric cryptography. Asymmetric cryptography has this benefit, but has a drawback, that is that needs more computational power. So symmetric encryption is easy to do, but it's not easy to, it has some drawbacks that asymmetric doesn't have, but someone has thought of how to use both. As a summary, let me show you which types of algorithms we can use in every kind of encryption. So for symmetric encryption, we have the algorithms AES, DES, OTP. AES is for advanced encryption, and OTP is for one-time path. One-time path is like the most secure kind of encryption that exists, because any kind of possibility to decrypt the message has the same probability. This comes from the information theory, where you can understand how it works. When every kind of combination has the same probability, it's almost, the only possibility you have is to guess the key. If you have millions of possibilities for a key, and each one has the same probability to be the right key, you will have a lot of work to do in order to break an encryption. So these are the algorithms used for symmetric encryption, and the right ones are the ones used for the asymmetric encryption. RSA, Elliptic Curve, and El Gamal are some of the most known names. RSA is an enterprise and has some of the patents to most used at this moment when using encryption in the internet. So maybe you have you know about it. Elliptic curve is a type of algorithm that with a shorter key than RSA has the same encryption power, but RSA is the most common algorithm used today. RSA come from the inventors that are Ron Rivest, Adi Shamir, and Leonard Adelman. They created this kind of encryption, but independently. Clifford Cox also created, but this information was kept secure because he worked for the UK government. Okay, so as there are symmetric and asymmetric, there is a third kind of type of encryption, the hybrid crypto system. So as I show you, for the symmetric encryption, we need a key every time, but it's easy to share the key. With asymmetric encryption, we can use the same key every time. So the hybrid crypto system use both benefits from both options. So we will use asymmetric encryption that is more secure to share the key that we are going to use for encrypting the message. So we are going to encrypt the message with the same key, but in order to share the key, we are going to use asymmetric encryption, like for example, RSA or the Diffie-Hellman key exchange. Okay, so at this point, until this point, we have the kinds of encryption. I hope these little animations could help us to understand and and you would like to keep searching about this, how this works. And next part is about a different type of problem. So I'm going to talk about the hashing function. So I'm going to show you with an example. Imagine we have a pineapple. If you pass through a mixer, you will obtain piña colada. So this is this piña colada has the same information as the original pineapple, but it's been reduced and put into a specific form. So this cannot be has any sense, but imagine we use that with data. So imagine we have a message, we pass through a mixer, and then we obtain a message of a fixed length with the original information. So for every message that pass through this mixer, we will obtain a different output with a fixed length. This cannot be helpful at this point, but using with the previous algorithms that we learned, we will have a very powerful feature to use in our processes in the internet. So one example is the HMAC. So H is for the hashing and MAC is for message authentication code. So we have a problem. How until this point we fix some of the original problems. So we can send messages in a secure way. So no other people that could have access to the message can read. For example, we fix the issue with intersection, we fix the issue with spoofing, but well, for intersection at least. But for example, repudiation and spoofing, how can we trust that someone that sent a message is the person that says, or that we are not open an insecure link? So here we can use the HMAC. So we can make the message secure, giving an option to see if the message comes from the person that the message says. So for example, if Alice is going to send a message, how can I know that that the Alice that we know is the one that is sending the message? We can use the message authentication code. So we are going to use the mixer, the blender, and we are going to pass the envelope through the blender, and we are going to generate a fixed length message. So the original message could have a lot of bytes, a lot of words, doesn't matter. But at the end, we will have a code with a fixed length that will represent uniquely the original message. Now, take a look that this message is already encrypted. So we are not going to pass the original message without protection. We are going to encrypt the message and then pass to the blender. We can see that then Alice is going to send the encrypted message and the hash message. If Bob do the same process, pass the encrypted message through the blender and obtain the same output, he can know that the message was not changed, was not tampered. So this is the object, the purpose of the HMAC. Next step is how can we use this process to be sure that this message comes from Alice. So at this point, we know that the message was not changed. We can be sure about that. If there is an intersection, we can detect and not open the message. But if it is if the blended value is the same as the encrypted value after blending, we can be sure that the message at least is not being tampered. Some of the algorithms that we can use for hashing are MD5, SHA-1, SHA-2, and SHA-3. SHA-3 is the latest, the more secure at this point. These algorithms are easier to break than the encryption algorithms. So this changes more frequently. At this point, this is the more secure. Okay, so using the previous concepts, the message authentication code and the encryption, now we can have a digital signature. Maybe you has known about this term, digital signature. So how can we trust a message coming from a expected person? We are going to use a similar process that we use for the asymmetrical encryption. We are going to have a key, a public key. Remember that previously we were using the public key to keep the message inside the box and then send back to Alice to open with the private key. This time, Alice is going to share the public key as before. Alice is going to write the message. So remember that previously, Bob was sending the message to Alice. But this time, Alice is going to send the message to Bob. So we are going to interchange a little bit the process. Alice is going to create the message, is going to blend the message using the hash function. Then it's going to encrypt the message with the private key. So the key here is the private key because the private key it's only available for Alice. So no one else can use this private key because the only owner of the key is Alice. Alice is going to encrypt the hash message. So it's going to be a easy step because this will have a short length, a fixed length. Then she's going to send the original message and the hash message, encrypted and hash message. So you can see that this does not work for encryption because the purpose of this is not encrypting the message. The purpose of this is show that Alice is Alice. How to show in the internet that someone is the one that she says? So we are going to use the digital signature. So then let's follow the example. So Bob is going to receive the message, is going to use the same hash function, and is going to obtain If this message has not changed, it's going to obtain the same value. In the other side, Bob also receives the encrypted hash message. This encrypted message can only be decrypted with the public key. But if these two values are the same, that means that this message did not change, and also that this message was encrypted with this key. So this message can only come from Alice because she is the only owner of this key. So after learning this, we can start to understand how something like the SSL TLS protocol works. So every time we try to access a resource on the internet and we need to share critical information that needs to be sent securely. For example, when you try to access your bank account or you are trying to buy something in Amazon, you need to send your password or you need to send your credit card information. So to establish a secure channel, we can use the SSL TLS protocol. There are two flavors, one way and two way. In this example, I'm going to show you how one way works. So first, we ask the server to identify how. We will be using a certificate, a digital certificate. The digital certificate is a file that has the public key and the digital signature in order to check if the signature is valid or not. The certificate is issued by a certificate authority, that is an organism that is trusted by both sides. So that authority is going to approve, it is going to sign the certificate, telling that the owner of the certificate is the owner of the domain. So if we check the signature and it is valid, we can send the information. We can establish the connection. This is known as a handshake, TLS handshake. When using two-way or mutual SSL TLS, not only the server will identify, but also the client will be requested to be identified. So this time we need to trust where are going to send the information, but also the server is going to only give access to certain clients. So the server identifies, send the certificate, and then we will send our certificate. This is like not as common as the one way. This is used almost in enterprise scenarios where this server is not publicly accessible over the internet. So after establish the handshake, we will be sending the information. SSL or TLS is a protocol created by Netscape in the early 90s to fix the issue of e-commerce transactions, to send private information over a secure channel. At some point, the Internet Standard Authority took the protocol and changed the name to TLS, that it is Transport Layer Security. This is a layer on top of the TCP layer of the OSI model. So the applications that are over the TCP and TLS can use this protocol to send information in a safe manner. Salesforce can act as a server and as a client. In each situation, Salesforce can request a certificate or send a certificate. Using single sign-on with SAML, for example, Salesforce will act as a server, so the IDP will request a certificate from Salesforce. This certificate is known as the API certificate. Normally, it's created when someone enables the first time the single sign-on, and this certificate can last 1 or 2 years, depending on the key size. This maybe some of you have seen an email that requests to renovate the certificate because it was expired. So this is a typical job for an admin, changing this certificate. This certificate can be self-signed, so signed by Salesforce itself, or signed by a certificate authority, normally paying for this. The certificate authority will send, we need to send the certificate to the certificate authority, and the certificate authority will send back the certificate signed. The certificate authority is a well-known organization that both sides can trust. In the scenario of Salesforce acting as a client, we can use outbound, we have outbound messages, for example, from workflow rules, or the other kind of single sign-on, delegated authentication, or an Apex callout to a secure endpoint. This time, if we are using, depending if we are using one-way SSL or two-way SSL, we will be sending a certificate or only requesting a certificate from the server. For the certificate that we send, it can be self-signed or signed by a CA. But for the certificate that we receive from the server when acting as a client, we will only accept certificates signed by a certificate authority. If you want to check which are the certificate authorities that Salesforce supports, you can use this trick. So let me show you. We can know which are the certificates that Salesforce will trust. So let me show you. I'm going to access a Salesforce org. I'm going to remove the last part of the URL, and I'm going to type cacerts.jsp. And we'll see a list of all the well-known certificates that Salesforce will trust for when acting as a client. So the certificates, the root certificates that Salesforce will use to verify the signature from the certificate that the server is sending to us. You can take a look. So let's continue with the presentation. So we were talking about certificate authorities, and we also talk about self-signed certificate. So how can we trust the certificate? Who signs the certificate? So the certificate authority is the one who signs the certificate. It can be me, myself, or it can be a certificate authority. For the certificate that we are using for application, the span, the life of the certificate can be from 30 days to 1 year normally. The organization that signs our certificate will have a certificate that which life is approximately from 5 to 20 years, and there will be a root certificate. So this is a chain of trust. The root certificate will sign the certificate for the signing authority, and then the signing authority will sign our certificate, so we can interchange over the internet. The root certificate will span from the life will be from 20 to 30 years. This is a very long time, and these certificates are normally installed on the server or in our computers. So we can see, if we access from our machines, we can see a list of all the well-known certificates. This is similar to the example that I showed you before with the certificates trusted by Salesforce. What is inside a digital certificate? So in order to use the certificate, the certificate will have the public key and also the information about the algorithms used to encrypt the signature. So this is a typical image of a certificate that we access clicking on the, for example, the browser. Let's go back to the browser. Here we can see a log. If we click the log, we see that there is a certificate, and this certificate is valid certificate. We will see information like it was issued to whom, in this case, Salesforce. it was issued by, in this case, DigiCert, and the valid dates from and to. So this certificate was issued from 1 year. We also can see the chain of trust. So our certificate was signed by the DigiCert TLS, and this certificate is signed by the global root CA from DigiCert. That this certificate normally will be installed in the browser, or we can install by ourselves. We will see, for example, the algorithm RSA, the key size to 2048 bits. Also, the signature, let's remember that the signature is the piece of data that we need to match, to verify, to be the same. And we also can see the public key. The public key will be used to decrypt the signature and check if it is the same as the one signed by the issuer. Now we can start the third part of the presentation, how Salesforce uses these technologies. So how the encryption affects our job every day. We will start with data encryption. So there are two kinds of data encryption. We have the field level encryption or the transparent data encryption. In Salesforce terminology, the field level encryption is known as the classic encryption, and the transparent data encryption is known as the platform encryption, also address encryption. So maybe you have seen that, or you see a detail on a record page, and some field has some characters masked, so you cannot see directly. This is the kind of field level encryption. But there is another type of encryption, that it is the address encryption. If you see the record detail, maybe you cannot notice that there is encryption at all. But because this is trying to protect a different resource, it's trying to do a different job. If the database is stolen from the data center, someone has physical access to the data and stole the data. With encryption at rest or platform encryption, the user cannot, will have access to some kind of data, but will not have access to the real data because it is encrypted. So these are the two types of encryption, data encryption available on the platform. This is also this can be also mapped to the Marketing Cloud product. In Marketing Cloud, we also have field level encryption and transparent encryption, and also other kind, the tokenized encryption. But the difference, I want to highlight the difference inside the Salesforce platform. So the field level encryption is included in the base user license. You can create an encrypted field every time. You need to see the problems that you will face using this, but you have this benefit for free. But the address encryption, that is that you can buy under the name of Chill, it is you need to pay an additional fee. The field level security encryption uses the AES algorithm, but with a 128-bit key size, whereas the Chill encryption uses 256-bit size. So 256 at the moment of this recording is a very hard encryption to break. So security will be assured using this kind of encryption. Let me show you with an example on the platform. Let's go back to the Salesforce org. Let's begin learning how to create a field and an encrypted field. So go to Setup, Object Manager. For example, I want to create an encrypted field on the contact object. If I click New, you can see that one of the options says text encrypted. You need to read the implications of using this kind of field. Next screen, let's say that we want to create a salary field. So the salary information is a value that needs to be protected protected. No, not everyone needs to have access to this information. Let's say the length is 8, salary, encrypted field, and we need to select which kind of masking we using. So we can use, for example, the credit card number. We can select which is the mask character to use. We can use the asterisk or the X. And here you can see an example. This is a typical example of how encrypted field looks, not only in Salesforce, but in outside Salesforce. Apart from this is a typical process to create a field. I'm going to add to every page layout. If I go now to a contact record and try to edit the field and save, we can see that there is no change. It looks like we can see all the value, but it's because I am an admin and I have a permission to see encrypted fields. So we need to test with a user that doesn't have this permission. Let's add more numbers and click save. Now we need to log in as the user. And if we try to access the same record, this time as the user doesn't have the see encrypted fields permission on the profile, on its profile, now we see the data mask. Okay, let's close the session as this other user. This is the classic encryption. So this is the more common kind of encryption. But let's see a different kind. So the second option, the shield encrypted. If we type encrypted in the setup, we can see that there are several options under platform encryption. If we go to advanced settings, we can select different combinations. We can try our own key, or we can use the key derivation function that Salesforce provides. The encryption policy. Here we can select which fields to encrypt, and if we want to encrypt files or shatter or encrypt indexes. So let's click encrypt fields. You can see which are the available fields to be encrypted. So remember, these fields, I can select these fields, but for a user, the field on the UI will not change. The field will be encrypted at rest. So if someone steals the database and try to replicate in a different server, cannot see the data because it is encrypted. If you encrypted, there are implications. So you need to check which fields are you need to encrypt. Normally would be fields with a personable identifiable information, or health information, for example, data that needs to be safe. So you need to encrypt all the fields. You need to be cautious about that. There are implications, for example, encrypting primary fields that are using as primary keys, as index searches, as indexes for searches. So let's check the information before encrypting. Anyway, you cannot do this in a production org if you don't have license, a shield license for that. About the key management, so we can generate a tenant secret, so a new key to encrypt the information to keep it secure, because even though we know that a 256-bit key, it's very secure with the computational power that we have, maybe can be exploited. So the other way that we have to keep the information safe is to rotate the keys to generate a new key, or you can bring your own key. let's continue. Let's go back to the presentation. So this is the first kind of application using encryption in Salesforce. But we can also use directly the algorithms. We can use the AES algorithm. We can create our own hash functions. So I have a demo using Apex for this. And I want to show you two possibilities. We can use the encryption algorithms using the Apex crypto class, or we can use a third-party library, for example, Crypto.js, that it is a JavaScript library. Okay, let me explain this demo. Here we can select the kind of algorithm to encrypt. And here, this is the key to encrypt the data. So imagine we want to encrypt this message. Hello world. I'm going to encrypt using the Apex crypto class using this key. Let's click encrypt. We see the output. It's not possible to know what was the original information from this string. If we copy and paste and we click the decrypt button using the encryption key, we will obtain the original message. We can use, we can obtain the same using the JS library. So hello world JS and click encrypt. We obtain a different value. We can obtain a different value every time I click the encrypt button. But it doesn't matter, because if I copy this value and using the same key, I click the decrypt, I will obtain the original value. But we can use this interchangeable. So if I encrypt something using Apex crypto class, hello world Apex, click encrypt and copy this encrypted value, I can decrypt using the JS library. Why? Because we are using standard algorithms for encryption and decryption. So let me show you how it works. This demo was developed using Aura components, but you can also use Lightning Web components. So I have a bigger component that hosts the JS and the Apex component. If we go to the Apex component, we have the input parameters, and we have the JavaScript controller. So it's very simple. We have an encrypt and a decrypt function. When using Apex, we need a controller. So the controller has all the logic. The Apex crypto class has some methods. So for example, if we want to encrypt, we will be using crypto.encrypt. We can use with managed IB or without the managed IB. IB means initialization vector. So as I show you in the demo, every time I click the value, the encrypt button, we will have a different output. This is because there is a random value that makes to keep using the same key. If we use the same key and the output is the same always, we are not using all the extent of the encryption, because with the same output, if we obtain the same with the same input, we obtain the same output every time. Someone with a lot of trial and error could obtain the original value. So you can see that every time I click, it changes. It is because the initialization vector. But in advance, in order to decrypt this information, I need to share the key, the key sharing problem that we saw before. But how can we share the initialization vector? So the initialization vector, it's at the beginning of the encrypted output, also known as the ciphertext. Let me show you how that is solved. So when using encrypt with managed IB, Salesforce solves that issue for us. It will create a random initialization vector and add to the output. Also, I'm using the crypto generate IAES key So for the encryption to work, we need a valid key. If you remember from the shield presentation, there was a key generation function. So generating the key is very important and needs to follow some rules. So we cannot create any key. We need to use a valid generation key algorithm. So from crypto, we have the generate AES key algorithm. If I change the algorithm, the key will change, because depending of the algorithm, if it is 128, 192, or 256, the key size will change. This is the number of bits on the key. You can see the extent of the encryption change. If I change the algorithm and try to encrypt, I will obtain a different output value. And we need to agree the encryption key and the algorithm in order to decrypt the message in the other side. So we have two functions, two methods, the decrypt apex and encrypt apex, and we simply are using the crypto encrypted with managed IB algorithm from the crypto class. You also can notice that we are using base 64 encode and decode. This output looks different, so this is encoded in 64 bits format. Now, if we go to the Crypto.js logic, we have similar implementation, encryption function and an encryption function, and the logic is based on a third-party library that we upload as a static resource, the Crypto.js library. Here, this is the library. You can access this from the internet, and all the kind of algorithms normally used are here. Okay, so if we go back to the JavaScript helper, we can see that we have similar functions, Crypto.js encrypt and decrypt, but this time we don't have the manage IB method from Apex. So remember that the IB is a random value added at the beginning of the ciphertext. This time we have to do an additional work to obtain that part, because if we don't have the initialization vector, we cannot decrypt successfully the ciphertext. So there are some kind of logic to handle, to take out that beginning of the message to obtain the initialization vector. I want to highlight that most of the hard work that we need for doing this was obtained from the blog of Enrico Murri. So at the end, I will share the links so you can check how it works. But basically, we are taking out the first 4 bytes, 64 bits from the message, and then using the key that is common for both sides and the algorithm, we can encrypt and decrypt successfully. So let me show you parts of the documentation. This is the crypto class documentation. We can see all kind of methods that we can use: signing, generating hash values, verifying HMAC values, encrypting and decrypting with and without managed initialization vector, generating AES key. If we go to the Crypto.js, it's a similar documentation. Is simpler, does not have a lot of examples. And this is the blog from Enrico, showing how to use the initialization vector from Apex to to make possible to encrypt and decrypt using or the Apex Crypto class or the Crypto.js library. You can use any kind of Crypto.js library. It is not the only one. For example, we have the Stanford JavaScript crypto library, but as soon as we agree on the encryption key and the algorithm, we will be fine. Let's go back to the presentation. The next demo, it's about creating and expire certificates. So let's go to the org, go to setup, and go to certificates. I have a certificate that was created automatically. You can see that the label no, that does not look like a manually created label. If we want to remove, we can remove this one as soon as this is not being used in any feature. We can see where it is used, accessing the certificate and hovering over the delete button. We see that this certificate cannot be used because it's being used in the identity provider. So if I want to remove this certificate, I'm going to go to the identity provider. I am not using the identity provider for this org. So at some point, the identity provider was enabled, but we don't need, we can disable. So the certificate now can be removed. You can see that we can click the delete button. Now we can create a new certificate. It can be a self-signed certificate or a CA certificate, CA signed certificate. For the self-signed, it will only ask a label, an API unique name. The key size can be 2048 or 4096 bits. Depending on how your org works, you can select the 2048 bits, but you need to change after 1 year. If you select the 4096 bits, you can change the certificate after 2 years because this is harder to break. Depending on the policies of your organization, you can select the encryption. Okay, I'm going to save. And automatically, Salesforce created for us a certificate. We can download the certificate and inspect. Or we can use directly, for example, in single sign-on. If we enable the single sign-on and we create a new single sign-on configuration for SAML, we will be using that certificate that we created. I'm not going to complete the certificate, all the process, but there is a great presentation on this topic by Lawrence Newcomb and Atul Ranjuru in the Apex Hours playlist. You can check. Now, let's take a look to the CA sign certificate to see what are the options. Again, we need a label, but this time we need to specify additional information. For example, common name. What is the common name of our company? Let's say my name. If in your country you have a segmentation based on departments, you can use that information. The email address of the owner, city, and country code. This is the basic information. And Salesforce will create the certificate request. So we can download the certificate signing request and send to the certification authority the certification authority will add their signature, and then we can upload. And after this, we can use, for example, in outbound messages, or we can use in Apex callouts to secure endpoints. Remember, you can use API or SOAP callouts. Okay. Let's go back to the presentation. And the last demo, it's about a different kind of application. We will be using a connected app, but in order to authenticate, it will be using the JOT flow from Salesforce. The JOT bearer flow that uses the JWT, that it is kind of a certificate using JSON. It is called JSON Web Tokens. So at some point, the JSON Web Token to be generated needs a certificate. It's a public key to sign the JSON Web Token. This is typically used when creating integrations between servers. When creating integration between servers, in order to obtain a token, we can use the JOT. So let me show you. I have an example. So I'm going to App Manager. I have already created a connected app for a Jenkins integration. If I click on View, we can see that we imported a digital certificate. So from Salesforce, this is an easy task. We only need to upload the digital certificate. If you want to check how an integration for continuous integration works, you can check also a presentation, a session here in the Apex Hours channel. There is a JOT and SAML assertion bearer flows. This is the episode for flows, identity flows. It was the speaker was Lawrence Newcomb again. So the easy part is to create the connected app, but how can we create the digital signature, the certificate? So this time we cannot use the user interface that Salesforce provides. We are going to use a different tool. We are going to use the openssl command line tool. This is a command line that has all the kind of algorithms to create keys, to generate hash, to create certificates, and we are going to see the steps to follow. First, we need to install the openssl command line tool. We can go to openssl.org and download the version for your operating system. In this case, I'm using Windows. I already downloaded the software and install it in a folder inside my computer. So if I go to Windows, I install it here at C:/openssl. I'm going to open the bin folder, and I'm going to open a command line tool from this location. If I click open, if I type openssl, I will enter into the command line of the openssl. I'm going to use some commands. I'm going to try to show you. I'm going to open a command line from this location, and I'm going to use a set of commands. The first one is to create a private key. So this is the command. So we are using openssl to generate an RSA key. we are going to output the key to this file, server.pass.key, and the key size is 22448 bits. You can see that a key was generated. We can see that this file was created. If we open this file, we can see what it's inside. Here we have, this is the key, the private key. This needs to be secure in the server, or in this case, in our computer, and cannot be shared outside. Okay, now after creating the key, we are going to generate a server.key file. So we are going to copy this command. Okay, so this time we executed this command to generate the server.key. So previously we created the key, but now we have a file .server.key. So it has the same information, but in a different way. So we can see only the key and some keywords at the beginning and at the end to indicate that this is the private key. Why this looks like this? Because it was defined by the RSI company. There is a specification that determines how this should be created. And openssl is the tool that follows those rules. Okay, next command is to create a certificate signing request. So remember from our previous example, when we created the certificate using the Salesforce UI, we created a certificate signing request in order to send to the certificate authority to be signed. This time we are creating using the command line tool. Okay, so the command says to create using the server.key, generate a server.csr file. So as before, during using the UI, we had to fill in some information. So this time, using the command line, we need to type similar information. So for country name, we are going to use CO from Colombia, state Bogota, locality Bogota, organization. Normally, this will be the name of the company. If there are organizational unit names, you can add. I don't have. Common name. The common name will be the domain that for which the certificate is going to be created. So let's say that I have a domain for elkincordoba.net. Email address. If I have an email to be contacted. We can add a challenge password if we want. It's preferable. Okay, and a server.csr file has been created. If I open this file, we can see that we have the certificate signing request. For the previous example, we will be sending this to the certificate authority, but we are not going to send to that certificate authority. We ourselves are going to sign the certificate. We are going to be the authority, because this is we can use a signed certificate, but the level of protection that we want to assure in our use case between Jenkins and this computer, for that scenario, it is enough to use a certificate signed by me. So the next command will be the next one. Let me copy paste. So we will be creating a certificate with the type of the certificate is X509. We will be using the SHA-256 algorithm for encrypting the signature. The number of days that this certificate will be valid is 1 year, 365 days. We'll be using the certificate signing request and the server key, the private key, and the output will be the server.crt file. All this kind of extension is defined by the RSA company. Okay, so we have obtained the certificate. It looks like a certificate. If we open, we can see what contains. It looks like a normal certificate issued it by me and issued to me with the time span of 1 year. Maybe this is not a certificate trusted by other applications, but in this case, is enough for using the Jenkins application. We can see that this is not trusted by the operating system because this certificate authority is not in the trusted certification authorities store. So the elkincordova.net is not a valid certification authority, but it doesn't matter for our use case. So we ended up with 4 files: a server file with extension CRT, a server.csr, a server.key, and a server.pass.key. We will be using only 2 of them: the server key, that is the private key, and the server file. So the server file we will upload to our connected app, and the server key we will upload to the server that we try to connect to Salesforce. So in this case, the Jenkins server. So if we go back to the app manager and the Jenkins app, we can upload the certificate here. I have already uploaded a certificate before, but as any kind of certificate, this certificate will expire. So we will have to repeat this process every time we have a new certificate. I can save. This will take some time to be expanded through the internet. Going to the Jenkins server, I can go to the credentials tab. And here I can see that I have a server.key. This is the previous one. Here also I can upload the new server key file. I can click update and replace with a new certificate. Then we will be using this ID in different stages of the configuration of the continuous integration job. I will not cover that part in this demo, but you can check the video on Apex Hours as I described it before. So going back to the presentation, we configure a certificate and a private key to be used in a JOT identity flow from Salesforce and an external server. So this is the end of the last demo. Finally, we have some useful links. as before, we have the openssl tool. You can check, you can download and try in your own computer. Next, we have the Digiser and the SSL Shopper. These are some tools that implement some of the functions of the openssl command line, but with a user interface. So for example, you want to check the status of a certificate for a common name, for example, salesforce.com, we type the common name and we can check if it is valid or if there is a problem with any of the intermediary certificates. Also, for the second link, we can have a certificate and paste the information and see and decode the information. Here you can see which is the command to execute from the openssl. The next link is the Let's Encrypt link. This is an organization that can sign certificates. So this is a certificate authority, and it is sponsored by one of the major companies in the internet technology panorama. So you can take a look. It is free. And one of the most important links is the certificate changes Trailblazer group. So here, any kind of certificate changes that Salesforce is going to do are published in advance for you to check. So I suggest you to join to the group. Finally, the references. So please take a look at the Cryptographic Principles for IT Professionals and Developers by Michael Perry, available at Pluralsight. Also, you can check the blog by Hari Krishnan for making authenticated web service callouts from Salesforce to IBM Cat's Iron using SSL certificates. There is a lot of a great detail, so you can check. The YouTube channel from Brit Cruz, Out of the Problem, has great examples of how this technologies works, and the app for Android and iPhone, the algorithms explained and animated by Moriteru Ishida and Yuki Mitsumori. This is a great resource for you to learn. So thank you for being with me during this time. I enjoy preparing the presentation. I hope you have enjoyed learning about these topics. Well, see you in the next opportunity. Thank you, Amit. Thank you, Apex Hour. It's a great pleasure. Bye.